So in this lecture, I want to continue our discussion about resonance structures before we jump back into allyl chemistry, because I just want to separate the ideas of like the rules for drawing resonance structures from what makes for a good resonance structure. So again, when we're talking about resonance structures, we're talking about different ways of depicting molecules. So bond line structures can only go so far, and if bond line structures can only go so far, what we need to do is actually think about ways to get us the distance to more accurately depicting what is actually going on with molecules. So resonance structures are different bond line structures for a single molecule. Each time we talk about these, if you notice, I've given you a slightly different definition, and that's because it's just not one of those things you can just like hear the definition for and completely understand what we're trying to do. But you can start to get better and better and more comfortable with seeing resonance structures and understanding their utility pretty quickly. So I'm going to look at both ways. Let's talk about some definitions in different ways, but also look at actually drawing these things. Okay. So we've talked about rules before. What I want to do now is ask the question, what makes for a good resonance structure? Or what makes a resonance structure good versus bad? That's a really good question. It seems awkward, but it's actually a really good question. So what we have to recognize is that resonance structures contribute to the overall structure of a molecule. They contribute to the overall structure of a molecule. Again, we have one molecule, we're depicting it with multiple bond line structures. Some bond line structures are better than others for these contributions. They don't go the distance necessarily and completely, fully, and accurately describe our molecule of interest, but they go a lot further and get a lot closer to the finish line than some other ones. Now, for example, if we consider a carbon-oxygen double bond, this is a carbonyl. It's actually a ketone, but generally a carbon-oxygen double bonded, a molecule with a carbon-oxygen double bond is a carbonyl. What we can do is we can push the electrons in one of two directions. We could push them up, and that would be route, I guess I'm going to the left, that would be B. So if I do that, I introduce a lone pair on the oxygen. I already had two lone pairs present, so now I have three. So draw those lone pairs like that, that's fine. Okay, so we're going to put a negative charge at this position. The carbon is now positively charged because it only has three bonds to it. Okay, so this is like us taking our alkene, moving the electrons to the right side or the left side, and pushing the electrons to the oxygen as opposed to the carbon. Now I could go the opposite way and say, let's push the electrons down to the carbon atom. So I go from the bond to the atom with the curly arrow, showing the movement of the electrons to make a new lone pair at the carbon atom. The oxygen atom up top now has a positive formal charge, group 6 element, -1 bond, -4 unshared electrons is +1. And the negative charge on the carbon atom down below, group 4 element, -3 bonds, -2 unshared electrons, that's -1. So I'm just moving the double bond in either direction. We've talked about how we could do that before. We tend to pick the side that's less substituted to fill with the electrons, because then the positive charge is at a more substituted position. But here we have a carbonyl, which is pretty different. What I'm saying is we could actually rank these in order of how good of a contributor they are. So rank the resonance structures. And we'll go from 1, 2, and 3. 1 to 3, where 1, that's the best. It's the best resonance structure and the strongest contributor. In terms of its overall structure, the best resonance structure is the best contribution to the actual structure of the molecule, and 3 is the worst, or the least contributing resonance structure. Okay, so if we rank these, it turns out that the answer is if 1's the best and 3's the worst, then it goes 3, 1, 2. Now, is that worth memorizing? Maybe. I'm going to need you to know how to do this on the exam. I'm not saying you have to memorize these numbers, but I want you to be able to look at these and rank them yourselves using a set of criteria that we're going to go over in a little bit. But what I'm saying is, if we look at the blue structure, that's the worst contributing resonance structure. It really honestly doesn't contribute that much at all. That is to say, there's not really too many times that carbon atom behaves like it's negatively charged. Okay, 1 is the best resonance structure. That is, that's the closest contributor to the actual structure of the molecule. It doesn't go all the way there. It gets pretty close though. That is to say, if I look at the structure of this molecule is actually acetone, and we analyze it all sorts of different ways using instrumentation that, we've talked about before, like IR, NMR, that sort of thing. If I analyze it, it looks like there's a carbon-oxygen double bond for the most part. Now, sometimes it behaves, particularly in chemical reactions, as though the oxygen is negatively charged and the carbon is positively charged. So that carbon-oxygen double bonded species that we've labeled with a 1 saying it's the best gets us pretty far. Like an IR world, when we take an IR, we know we've got this carbon-oxygen double bond, at least something in that looks and smells like it. But when we do chemistry, we see that the oxygen behaves like it's negatively charged. The carbon behaves like it's positively charged. Never really behaves like the opposite with that blue structure. So my point is, if we wanted to pick acetone, we really want to use 2 resonance structures to describe acetone, the 1 and the 2. Number 3 doesn't really get too involved, but I guess it's possible in some circumstances. So to most realistically describe acetone, we could say, oh, that carbon-oxygen bond, it's mostly double bond in character, but has some positive or some single bond characters. So it's not like as tight as normal double bond. It's a little bit, well, I won't go there. What I will say is if we treat this with something that's positively charged, we'll see that positively charged atom adduct most likely to the oxygen. Negatively charged atom will adduct most likely with the positively charged carbon, or the carbon atom that has some positive character from resonance structure too. Okay, I'm going to stop talking and just go on to another example. Let's look at the example where we went over this resonance structure last time. It's one of my favorite ones to consider. 2 lone pairs on the oxygen atom, the central oxygen atom. We can push 1 over to the right. That's going to give us this structure. And that would then have a positive charge here, or we could go to the left. Now, it doesn't matter which lone pair in this depiction. We could get into some orbital stuff to show that one lone pair is preferred over the other, but they're interconverting and that sort of thing. So anyway, if we consider an alternative resonance structure, well, if I had to rank these, if I'm going to rank them, I'm going to say that this one up top, this is ranked NA. It's not a viable resonance structure. We've talked about why. It turns out that I break the octet rule at the left carbon atom by giving it a 5th bond. So it's not like it's the worst. Being worst is still meaning it's real. It's just not as good of a contributor as the other structures, not in, many cases. But in this left-handed structure that I show in blue, that breaks rules. Okay, it breaks the octet rule. Okay, it's not even a viable resonance structure. It's like me saying, okay, I'm going to start from the middle structure and go to something that has, a 6-membered ring. It's like we didn't even have enough atoms to make a 6-membered ring. Okay, so it's just not even real. Whereas the structure on the right is actually, in this case, number 1, and we have number 2 in the middle. So the structure on the right is the best. Okay. So sometimes it's not so intuitive why we have a best and a worst. Okay. In the first example with acetone, it makes sense why the middle structure is the best. If I told you, okay, give me the structure of a molecule that has the formula C3H6O, many of you would give me this structure or something very close to it. Move the carbon-oxygen double bond around, I guess. But, so many of you would give me this structure. It's a really good structure. That's a really good structure of acetone. Like your organic one thinking would lead you to that structure. And there's a good reason why we draw that as the bond line structure. It's the best contributing resonance structure. It's just sometimes we have our intuition misleads us, and the molecule behaves as though it's got a carbon-oxygen double bond with an oxygen negative, carbon positive. Okay, so that's what we're trying to learn with resonance structures. Now, down below, it gets less intuitive. Okay, if I said, give me this molecule and put a positive charge in there, it's not clear that all of you would give me the right structure for the best structure. It's just not intuitive at this stage. So let's look at some criteria. So the best contributor is the one that most closely represents the actual structure of a molecule. Let's talk about some rules for prioritizing resonance structures. And these are listed in order of importance. Okay, so number one, resonance structures where all atoms have an octet are the best, are better. Resonance structures where all atoms have an octet. Highlight this one like crazy. This is a really important rule. When you're looking at resonance structures and trying to figure out if they're the best, I'm saying resonance structures where all atoms have an octet are the best. Well, you might say, wait a second, last time we talked about rules for even drawing resonance structures, and you said you can't break the octet rule. That's not what I said. I said you can't exceed the octet rule. You actually will sort of violate the octet rule in many cases when you're drawing resonance structures. So for example, if we've got these resonance structures, back to acetone, okay, if you look, we don't have 8 electrons at the carbon atom in the right-handed resonance structure. Does that mean that the right-handed resonance structure is a wrong resonance structure? No, it's a fine resonance structure. It hasn't exceeded the octet rule. It's fallen short. It's at 6 electrons, not 8. So falling short is okay. It's just exceeding it that's terrible, and we can't do it for these row 2 elements, which is what we use. Now, what that means, though, is that it's just not as good as the one where everything has an octet. That would be that structure on the left that I've drawn, okay? The typical structure of acetone. So resonance structures where all atoms have an octet are the best. And what do I mean by best? I mean better contributors. Now that's the most important rule when you're drawing resonance structures and you have to rank them in order of which is the best resonance structure. We would say the best contributing resonance structure is the one where all the atoms have an octet. Okay. Next, so number 2, not as important as number 1, is structures with less charge separation are better. So charge separation is just another term for charges are present at all. Okay, if we again look at, these are really important resonance structures, so I don't mind redrawing them. But if we look at acetone versus the other structure, we would say that this structure has charge separation. Okay, so it has charge separation. It's not as good as the other structure, which is the best. You might say, well, wait, why do I even need to know this? Because the other structure, everything has an octet. Well, sometimes it's a little bit kind of tricky to see. Let's say we've got our allocation again, and I move the electrons. Instead of moving the electrons from bond and swinging them over to make a new bond, let's say I jump them into an atom to make a lone pair in the central carbon atom. That's the negative, and we have pluses on both ends now. This is still the best resonance structure. So, and maybe you could make an argument that even in that case, you're losing the octet rule at the left-handed carbon atom. So now you have 2 carbons without an octet rule. Sure. Okay. It's a nice rule to show. Now, let me just emphasize, though, that there are cases where resonance structures can be the same priority, the same equal goodness in terms of what they contribute. We'll get to that at the end. So, even if this one isn't that helpful because something already is losing its octet, which isn't great, it at least provides separation from rule number 3, okay? The third rule, which is after rules 1 and 2, which is the one that I don't want you to think is most important. Just can't emphasize that enough. And the reason why I'm making a big deal about it is because many people do emphasize it too much. And that is, if you have charge separation, put the negative charge, or I'm not going to give you rules. I'm going to tell you what makes things a better resonance structure. If you have charge separation, structures with a negative on electronegative elements and or positive on electropositive elements are better. Okay, that is to say, if you have a negative and a positive present, the one where the negative is on the electronegative atom is better. Okay, so let's look at an example of this. Let's start with acetone, and we're going to push the double bond in either direction. Once where it goes, the electrons go up and onto the oxygen atom, leaving behind a positive charge on the carbon atom. Then we flip that around. Now you might recall that the oxygen is more electronegative. That makes the carbon by default more electropositive. So this left structure is not as good. We would say that's the worst. That's the worst structure. And then that right structure is better than the left structure. The right structure is better than the left structure. So I'm going to write best there, right? No, I'm not going to write best there. I'm going to write best on the one where the important rule, the rule with the octet rule, is taken into account. The octet rule dominates here. Okay, and you're like, I get it. Okay, the middle one's the best, but that's helpful to know where number 2 is, right? That helps me to rank number 2. So Willoughby, why are you making a big deal about this? I'm making a big deal because when people see stuff like this molecule again, okay, when students see this molecule, they forget the ranking of the rules, which is important because they'll be like, that's the best resonance structure. That's a way better resonance structure than the one where you've got a carbon-oxygen double bond, because the carbon-oxygen double bond soaks up one of the lone pairs of electrons on the oxygen, leaving behind a positive formal charge on the oxygen atom. So this one's the best because the positive charge is not on the electronegative element. It's on the carbon atom, the electropositive element. And I'm like, no. This one on the right is the best because everything has an octet. I'm sorry about that. Everything has an octet. So that one on the right is the best. Everything having an octet is more important than where your charges are at. Okay? Priority number one. I don't care where the negative is if everything's, if you can draw something else where things are have a full octet. Okay. Before my pencil runs out of batteries, I just want to emphasize again that resonance structures can have equal contribution. And we would say they are degenerate. Degenerate or of the same energy. And the energy that we're talking about here is potential energy. So I'm just going to go ahead and write that in. Okay. So resonance structures can have equal contribution. Well, when do they have equal contribution? You actually know this a lot better than you think you do. These would be resonance structures where you, like in your organic one constitutional isomer mind, want to rotate them around and tell me that they are duplicate structures. Okay? So in this case, if we look at both of the resonance structures of our allyl system, we don't have substitution around. If we had substitution, like if we had a prenyl group, two methyl groups on one side, then it matters which one, where the positive charge is. But here it doesn't matter. So this is not the case for prenyl, and I'll leave you to look that up. But for allyl, where both sides are the same, it doesn't matter where the positive charge is in terms of its stability. But it's important that we know that both structures exist, because that's helpful. That tells us that, you know, the left side behaves kind of like it has a double bond and kind of like it has a positive charge. And you're like, wait, that doesn't make sense. How can you draw a bond? How can you draw one bond line structure to show a positive charge and a double bond? I'm like, I can't. That's why I draw two bond line structures. Okay, maybe you're not following, but let's remember our favorite use of resonance structures, and that is when we look at the benzene double bonds. I don't know if you remember this, but in org 1 I said, don't worry about when you're drawing benzene for me where you put your double bonds, just as long as they're alternating double, single, double, single, double. Okay, now the reason why is because it doesn't matter because of resonance structures. If you look, these two molecules of benzene are just resonance structures. We've moved the double bonds around in either case. So you can actually zoom in on this, and you could roll, I'm going to draw this nice and neat down below. You can take one benzene molecule, and you can roll the double bonds around either clockwise or counterclockwise. You have to move them all, otherwise you start to break octets. So you move them all simultaneously, and you get a new structure, a structure where the double bonds have repositioned themselves. If I'm moving electrons, but not moving nuclei and not breaking sigma bonds, I'm just considering different distributions of electrons within the same molecule. So which one of these, the left structure or the right structure, is benzene? Is benzene on the left or is benzene on the right? The answer is yes. These resonance structures both contribute equally, it turns out, to the overall structure of benzene. Does benzene really have a carbon-oxygen single bond sometimes and a double bond sometimes? No, it has a carbon-carbon 1.5 bond, it turns out. We'll look at that more in maybe this module. I don't really know. It's coming soon when we look at aromaticity. So it turns out that we have to average these two structures because they have an equal contribution. You can weight the two structures if you really want to get into it. They would be a 50-50 weight in this case for the most part. All the other resonance structures are less than like 1% for them in most cases. But that gives you a sense of resonance structure. So hopefully you found this little module helpful, or this little kind of side whatever into resonance structures helpful, at least for the lab on resonance structures, the first computational lab. So anyway, I'll end there, and then we'll move back into allyl chemistry. Okay, have a good one, everyone.